All right, you're gonna miss all the great stuff. All right, so I just started the stream. Let's see if this bad boy works. Real pros are made of computers. I'm a computer. There we go. Cool. Can you guys see the screen on the Discord?
Yeah.
Cool. All right. Oh, can you see presenter mode? That's weird. Can you see normal stuff? Can somebody confirm? Can you see slides?
Yep. It looks fine.
All right, awesome, thanks. Oh yeah, let me put up the Discord stuff, man. I need like 5 monitors to actually do this stuff properly. Um, okay, yeah. So great. So we did the call for a flag challenge. So the idea there was to get you used to calling functions and starting to learn a little bit more about that. Um, what we're going to continue to do is first, let me turn that off, make sure that doesn't mess up. Ba, ba, ba. Check. Yes. Okay, cool. Okay. So, and we looked at, and we talked about, okay, so we can use the stack for when we're calling a function, we push arguments, or no, uh, we put the parameters in registers. So those are the things that we use here. And so the question we kind of want to ask is, well, what if our function needs more variables than we have registers, right? So as you're writing programs, you might write a function that takes in multiple variables. We're talking like uh, 10, 20 variables. The whole point is that when you're writing your code in a high level code, you're not restricted to how many registers the CPU has. So you can only have functions that are that size. And so that's one of the big benefits there of having that. So what we can do is we can actually reserve space for us on the stack for variables that are local to our function. That way, we're not constrained by how many registers our CPU has. We can actually use any number of variables. And we actually did this. If we go all the way back to when we were doing the echo.s program, right, we had this little snippet of code. And the main thing is the very first thing we did was we created 100 bytes of space on the stack by subtracting the stack pointer down by 100. Why did subtracting the stack mean that we reserved space on the stack? Yeah, because the stack goes down, right? So the stack starts at high addresses and moves down. So when we want to reserve space on the stack, we adjust the stack down. Excellent. Um, cool. All right. Well, I needed to do something real quick because I just realized I got a lot of stuff here where I'm asking you for questions, and I want you to be able to get those answers. All right. And yes, if you're looking in the lower left, I do have 90 slides. I think we actually could get through most of them today. Okay, and then we go back. All right, cool. So now we're back here. So now we want to access our function's local variables. So let's say that we want to write a function with two local variables, bar and foo. And rather than worrying about what register they're in, we'll just write this. So we'll use a label, x86, we'll call something a function. The first thing we're going to do is subtract 8 from RSP. And I just realized that is not enough space. Oh no. This is great. I love fixing slides on the fly. All right. There we go. Cool. Okay. So we're using two variables. Let's just call them integer variables. And so let's say that our variable, I actually just realized I didn't, whatever. Let's say that the variables are 8 bytes each. So we have 16. So what we're gonna do if we want to store two variables, each of them 8 bytes, we're gonna need to reserve 16 bytes on the stack by subtracting the stack down by 16 bytes. Then what we'll do is we'll store some values into that location. So now that we've subtracted from RSP, the stack is growing down. If we index up in the stack pointer, we should be able to see that. So let's see if I can quickly, crappily draw this. So let's say RSP was originally here at the start of the function. Each of these will be 8 bytes. So we'll move down 8 and down 8. Ooh, it's not getting great. So subtract 16, the stack pointer now points here. So if we move hex 20 into RSP plus 8, where's that value going? Which cell in my diagram? So stack's growing down. So this is high memory regions and this is low. So it should be 0x20, right? If we said, okay, subtract by 16, it's pointing at the start here. So plus 8 from that should put pointing here. So it will be this cell here. It kind of always depends on how you actually draw this stuff, but I think we'll be able to get that. And we'll see this with better examples of this. And this is actually a really good skill. This is something that I do when I'm thinking about how to exploit a vulnerability, is actually draw like the stack layout in something like this, and I see, okay, what variables are where and what things can I do here. So the next one is going to move, the next instruction is going to move hex 10 onto RSP. So there's no plus 8, so there's no shift. We know based on this diagram that the value in RSP points to wherever this arrow points. So we do 0x10. And so which of these values is bar and which one is foo?
We don't know
Why don't we know?
because there's been nothing to tie the name bar and the name foo to either of those positions.
Yeah, somebody's messaging CDecal in the Discord. What do you think about that? What was CDecal for? Yeah, so CDecal is for calling functions, right? So that's when we want to call a function, but that's in CDecal. We are actually using in x86-64 on Linux, the System 5 ABI. I think that's. So we're actually using the System 5 calling convention. But fundamentally, because we didn't actually call anything, calling conventions don't come into play here at all. So yeah, we actually have no idea which one's bar and which one's foo because we don't know what our intention is here. Are we supposed to set bar to hex 20 or foo to hex 20? And so that's what would tell us. So that was kind of a trick question. We could just say, if the code kind of looks something like this, foo is equal to hex 10. If we knew that bit, then we would say, aha, this must be foo, and this must be bar. Okay, cool. Now that we can define them in this way, now, but there's a bit of a problem. So let's, using the stack pointer. So just like before, we subtract 16 bytes. We then move hex 20 into RSP plus 8. And we move 10 into RSP. So this was bar and this was foo. Some other stuff happens. And then later on in the function, we move 100 into RSP plus 8. So which value changed, foo or bar? So remember, let's just say this is bar and this one's foo. Bar changed. Why did bar change? RSP plus 8 is where bar is. Is it though? How can you guarantee that? What if inside of these ellipses, I had something that said push RAX? So push RAX does what? So let's draw our diagram again. So we had boop, boop, boop. The first one, bar, is at 0x20. RSP points here. 0x10. So push RAX. So what's going to happen there? How many values down? How is the value of the stack pointer going to change after this?
It'll shift down the size of the register.
Yeah, it'll change
RAX
RSP. No, it doesn't change RAX. It implicitly changes the stack pointer. Yeah. So the stack pointer gets moved down 8 bytes, and whatever was in RAX, we don't know what that is, gets put onto the stack. Now when we calculate RSP plus 8, what does that point to? Bar, foo, or whatever was in RAX? Yeah, now this points, RAX plus 8 points here, which is foo. So the point here is that actually by using the stack pointer, we can't know what value has changed because the stack can change while the function is executing. If we are using temporary values and things, the compiler can decide to store some variables onto the stack and then pop those off later. As long as our function, when we leave our function, the stack is at the same location, then we will be okay. And then we'll be okay and we know that it won't change. And so because of this, it actually can be difficult to understand what variable is being referenced because you don't know what RSP plus 8 means unless you are keeping track of all the possible changes to the stack pointer. And so this is the, oh, that's fun. So yeah, this depends on if RSP has changed. And so this is why there's actually another register that's typically used to do this. This is called the base pointer. So base pointer, you can think of it as BP here. So the base pointer is the thing that actually will be a constant value that will point to the start of what we'll get to in a second is your function frame. And that's the memory on the stack that kind of your function is responsible for. Now, compilers are very smart, and so as they get smarter and smarter, sometimes they will actually use the stack pointer to do offsets depending on different optimizations. So you may actually see that. So don't get super confused when you see stack pointer offsets being used. Okay, so we can look. So now, if we're going to use the base pointer, the first thing we have to think about is, okay, we're a function. The function that called us has some base pointer set. So what our responsibility is if we're going to overwrite this register RBP, just like there was a set of registers that we looked at that in system V calling convention that are used. Let me see if I can find those. That would be cool. Can't remember exactly where we looked at that, but yeah, what registers can we use? Here we go. So if the callee wishes to use the registers RBX, RSP, RBP, R12 through R15, it must restore the original values before returning to the caller. So this means, hey, if we're going to set up our own base pointer, we have to save it for the person that called us. And how do we save that? Well, we have a very nice way of doing that. We have the stack. So we can actually use the stack here. So we can first push the base pointer onto the stack. So the very first thing that we do is push RBP onto the stack. We don't know what that value is. The next thing we do is we move wherever the current stack pointer is into the base pointer. So this is setting up the base pointer for our stack frame or our function frame. And then we're going to subtract 16 from the base pointer. So we can see that wherever the stack pointer was, the base pointer pointed to where it was at the start, almost to where it was at the start of this function, and then moves down 16 bytes of the stack pointer. And now we can rather than using references from the stack pointer, we're going to use offsets from the base pointer. So we'll kind of walk through this. So let's draw the stack. So if the stack pointer originally pointed here, the thing that happens is RBP is copied onto the stack, and the stack pointer now points here. The next thing that happens is the stack pointer moves here. So I'll draw, I think I switch it later, but we'll draw RBP is on the right and RSP is on the left. And I don't think I can erase with this stupid thing. Then we're going to subtract 16. So 2 more of these cells. Boom. Boom. And then we're going to move 20 into RBP minus 8. So where is RBP minus 8? Yeah, the second cell, perfect. Yeah, so it's the exact same layout. We're just using a different, so this would be OX20. Cool. Glad I did all that work to make it so this went a little bit better. Anyways, move that into 20, RBP minus 16 into OX10, and so on and so forth. And now when we move RBP, this should be RBP minus 8. When we move RBP minus 8 into 100 there, now is there any ambiguity, assuming that the base pointer address hasn't changed, is there any ambiguity as to where this 100 hex goes? Exactly. No, we know that we're overriding RBP minus 8 is this one. So we're going to change that from hex 20 to hex 100. And we'll need to do some cleanup at the end. So we actually need to make sure the stack is consistent. So just like we actually just looked at before, we need to make sure that the value in RSP is the same from when we're called. And we also need to make sure that we put RBP back to the same value. So what'll happen is, and this is an important concept when you're looking at functions and you're looking at assembly language, almost every function will have this. It'll have a function prologue. So it'll have some instructions that it does. It will push RBP, move the stack pointer into the base pointer, and subtract whatever things it needs from the stack pointer. So that's the function prologue. And then it will do some stuff, the actual content of what you want to do. And then at the end, there'll be the function prologue that reverses these steps. So what leave does is leave, and we'll walk through this, but leave sets the, copies the current base pointer to the stack pointer, so moves the stack where the current base pointer is, and then does a pop RBP, remember, because we first pushed RBP onto the stack. So we pushed it onto the stack. So this leave instruction, you can think of it as undoing these first two instructions here. So it undoes the move RBP RSP and the push RBP because it moves the base pointer back into the stack pointer, and then there's a pop RBP, all in one nice little instruction. And then after that does a return. So after then, the ret instruction, like we said, is the opposite of call. It's the thing that takes you back to whoever called you. And actually, you can think of ret is almost, not even almost, it is identical to a pop RIP. So that is take whatever RSP is currently pointing at, copy that value into the instruction pointer, which is where you're going to start executing next, and then increment the stack pointer by 8. Cool. Okay, this is slightly incorrect, but one thing that you can use when you're doing this is, as you're reverse engineering code and looking at x86-64 assembly code, you can reuse the base. So if you have negative offsets from RBP, then you know that those are local variables. Parameters are usually will either be positive offsets of RBP if they've been pushed on the stack, but in the System 5 calling convention, this is actually more often than not, they'll be in those registers. So you'll see, oh, this register was never set, which means it must have been somebody that called us. No, ret is identical to pop RIP. So RIP, the instruction pointer. Cool. And then we can take a little example of this using actual code from some stuff that I compiled. So this is, I think I deleted the code, so it's good because we don't really care about it. We could walk through and see exactly what happens here. So what are we doing this here? So we're move the stack pointer to the base pointer. We move hex A into RBP minus C, hex 64 into RBP minus 8. We're moving a relative offset, so RIP plus hex A0 into XMM0 register, moving that into RBP minus 4. We're then moving RBP minus 8 into EAX, and then moving EAX into RBP minus 0x7. So we're just going to walk through what that looks like. So we have the stack, and let's say that the stack happens to be hex 10,000 right at this location. So what this means, remember, when we're drawing these arrows, is that all this means is that the value of hex 10,000 is inside the RSP register. So it's kind of it's hard to tell who's correct here in the sense that, like, we don't really care where the arrow points. The arrow only points to whatever that value is inside here and inside RSP. Let me check what's my computer doing? I think we can discard those annotations as good as they are. Oh, cool, it's completely pegged. Awesome. OBS, what are you doing? I swear I streamed for a while and all right. So RSP is not the start of the function. RSP is just the pointer to where the stack currently is. So the other arrow here that's pointing to the start of this instruction means that the instruction pointer, so RIP, points to wherever this instruction is in memory, and this means this is the next instruction that will execute. So again, why doesn't it? Oh, I think I got rid of the pushing RBP and the cleanup and stuff. We actually should have that, but anyways, we'll just walk through this code because it's just code that we can look at and walk through and execute and reason about what it's doing. So the very first thing we're doing is moving RSP into RBP. So that's the first thing. So now we didn't know before what RBP is. Now we know it's the exact same value as RSP, in this case, hex 10,000. The next thing we're going to do is move A into RBP minus C. So we take RBP, which is 10,000, subtract hex C from it, and then copy A into there. So that goes into FFF4, right? That should be C down. But what just happened? So it seems like this is incorrect. So what did we say about the stack? What in the stack is usable? So if I told you the stack pointer is at hex 10,000, what memory can you read and write to, and which ones can you not? Yeah, so everything above greater than RSP is good. Everything after that is garbage. But this stupid program that I compiled from GCC actually does this and uses memory even after the stack pointer. And the reason is that you won't see this in just regular x86, so 32-bit x86, but x86 64 defines this concept of a red zone where 128 bytes after RSP are considered safe, which means that it's not going to be modified by interrupts, exceptions, or signal handlers. So this means if your compiler, if you're writing a program and your function doesn't call any other functions, then it doesn't, and it uses less than 128 bytes, it can actually just use that information on the stack without allocating any additional information. So this is kind of a really cool, you can see this is like this as an optimization where they have this crazy optimization that's going on that only occurs in these certain cases. But it makes the programs faster and smaller, so that's why they do it. So, okay, now that we got that, that is the red zone is below the stack pointer. And so we can write there. So we're going to write A into RBP minus C. So hex A goes into where FFF4 is. The next thing we're going to do is move 64 into RBP minus 8. So 64 will go there. We'll move this into and the value that just happens to be there is 41273333. I can't remember what this is. It's some representation of a decimal number or a float. So floats and decimal numbers get represented obviously still as hex. You can read about all the magical cool stuff there. The next instruction, we're going to move what's in that register to RBP minus 4. So we take that, move it into RBP minus 4, which is FFFC. And then we're going to move RBP minus 8. So RBP minus 4 minus 8 is hex 64, moving that into EAX. So the RAX register is now hex 64. And then we're going to add what's in the EAX register to whatever's at RBP minus C and then copy the result into RBP minus C. So this will move 64 into RBP minus 4 minus 8 minus C. So this will do hex 64 plus hex A. So it should copy that there. So that is 6E apparently. So that's a good thing to know. And then it'll just continue on and execute whatever instruction is next. Questions on that example? So no, not after the red zone. We didn't talk about memory layout, but effectively the instructions, where these instructions are located, is in a very different place than the stack. And it technically, and depending on how the program is compiled, where the instructions are actually get randomized every time the program is run. Yeah, we can get into we'll get into more of those details later. Cool. Let me check something real quick. Okay. All right. So now with that, we kind of actually have our full System 5 calling convention. So the caller, when we call a function, first puts the first 6 integer pointer arguments in the registers, RDI, RSI, RDX, RCX, R8, and R9. Then any additional arguments are pushed onto the stack, just like the key difference here with CDECL, all arguments are pushed onto the stack, so no registers are used. Then the address of the instruction after the call is pushed onto the stack. We'll look at this in a second. And then the callee, so the person who gets called pushes the previous frame pointer or base pointer onto the stack, creates space on the stack for local variables, and then ensures that the stack is consistent on return and puts the return value in the RAX register. So this is basically everything you need to do this. Cool. And now that we are here, what the heck is going on? All right. Closing that. Cool. Okay. So now we will look at, the animation is all messed up. Okay. You know what, why don't we just fix it? All right, let me just fix this real quick, and then we should be good. Okay, 28. I want that to go where 7 goes. That's okay. You don't have to connect to that. Okay. Yeah, whatever. It's good enough. Yes. So the question is, if you have a function with a bunch of arguments, args 1 to 6 will be in registers, and args 8 and after 7. So first arg 7 is pushed onto the stack, and then arg 8. So it'll be that 7 will be higher up. Oh, is that right? Let me look. I got to look at the calling convention. Yeah, right to left. So exactly. Okay, yeah. So it'll first be, so yeah, first argument 8 is pushed and then argument 7. So as you're going up the stack, you'll go argument 7 and then argument 8 and then argument 9 and argument 10 and so on up the stack. Cool. Okay, so we have, this is just some C code. It's incredibly simple. You can actually think about it as Java. I mean, it doesn't really matter what's going on here. I'm just showing you some code that we've written that then is compiled to assembly, but you could have written this assembly yourself because we've gone over all the basics of how this assembly stuff works. So So we have a function main, we have an integer a, we're going to call some function called callee, we're going to pass in the parameters 10 and 40, set that to the integer a, and then return a from main. So the function callee is a very simple one that just takes two parameters, a and b, returns a plus b plus 1. So any questions on what this code does or should do? What should main return? Oh, there's a fight. Yeah, so 10 plus 40 is 50 plus 1, 51, so it should be 51. Excellent. Great. Okay, so let's look at first the main function. So we should see the main here. So, okay. So we'll first look, and we're actually going to do the same thing and step through these exact instructions to see what they do on like a kind of simulated CPU. So I think this should help kind of convey some notion of what's going on. So the very first thing we're going to do is to save the base pointer. So we're going to push RBP, move the stack pointer to the base pointer, subtract hex 10 from the stack pointer, which is 16. We're going to move 28 into ESI, A into EDI. So that's setting up the parameters, call the function callee, and then we're going to move whatever. Now, again, according to the calling convention, once we call the callee function, we know that we get the return value in the RAX register. So then we take the RAX register, put it in RBP minus 4, and then we do RBP minus 4 into EAX, leave, and return. So why do we do this last move RBP minus 4 into EAX? What's that doing? Yeah, so it's putting the return of main into RAX, exactly. But why, isn't this kind of stupid? Like, look at these two instructions. What do these two instructions do? Take whatever's in RAX, put it into RBP minus 4, and the next instruction, take whatever's in RBP minus 4 and puts it into EAX. Do we need these two instructions? We don't need the second one. Do we even need the first one? Yeah, technically no, since callee will put whatever its return value is into RAX, and then as long as we leave that value in RAX, then it will be properly returned. Yeah, so the function callee saves the result into RAX, and if we're just returning that from our function, then we can just leave it in RAX. But so the question is then, why does it do this? So come on, computers, like computers are smart, right? Compilers are smart. Why does it make such dumb code? Ooh, because the value could change. It could, but it doesn't here. So why isn't the computer smart enough? Why isn't the compiler smart enough to know that A doesn't change here between these two instructions? Nope, doesn't need to consider any thread safety possibilities. because the compiler knows that this A is only used in this function. Yeah, so there's a couple different reasons. So some of the reasons why you came up with. So maybe A is actually a variable that could change between here, depending on if it's I don't know, a pointer, there's many threads that have access to it or something crazy. You could think of a situation. Yeah, the main is because I didn't put on any optimization. So the compiler didn't do any optimization passes, which I think it would be able to figure out and would actually just remove these two lines of code. But this is kind of a good thing to think about and to take into your mindset is that it's possible to be too smart, and this is why compilers by default will usually compile something without optimizations, because right now we can actually see there's like a one-to-one mapping here. So we have the function, the first three lines of the function prolog, the next three lines set up this call to the function callee, so that's that function call. The next line of assembly puts the result into the variable A, and this next line of assembly does this return A, so puts the value back into EAX to do the return, and then leaves them returned. So it's actually really easy to kind of convince yourself that yes, this assembly code does do what this function says because it's not doing anything fancy. And you can see there's like a one-to-one mapping. So this is actually a good, I think it was Carmack. John Carmack, the guy who did id Software and Doom and stuff. He was talking about when he optimizes a function, he first writes one that is incredibly slow and stupid, but is correct. And so he has the function that is correct and then replaces that with one that is maybe fast or optimized, but he makes sure he keeps the other one around so he can compare the results to make sure the function doesn't fucking mess up because his optimizations actually broke things. So it's actually a good thing to get into with programming is like, okay, let's try not to be too clever. Let's actually do the thing that's correct. Make sure that the code is correct, and then later you can speed it up. So it's something interesting to think about. Okay. So this callee function, pretty simple, stores RBP, moves the stack pointer to the base pointer, moves EDI into RBP minus 4, moves ESI into RBP minus 8, moves RBP minus 4 into EDX, moves RBP minus 8 into EAX, adds EDX to EAX, stores the result in EAX, and then adds 1 to EAX. So we can see here we're doing the 1. And then we pop RBP. So we then are going to pop do the opposite of this push RBP and then ret. So how come this callee has a pop RBP and main has a leave? In the function epilogue. Not quite. So actually main is returning to whoever called it. So main has a ret just like callee. So it's not about who or what is calling them. What the heck? Why does that look so terrible? Oh no. So the returning to the main address is done by the ret instruction. So the ret instruction in both will return to whoever called it. Yeah, exactly. So main is clearing. So the key difference between the two, if you look at the function prolog, is that main subtracts 10 from RSP, whereas callee doesn't do that. So this is actually just another, it's an optimization from the compiler where it knows, okay, in this function callee, it doesn't call any other function. So this is why it's able to reuse the, this is why it's able to blah, 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 blah. Yeah, main calls callee, which means it needs to reserve the stack space. In callee, it uses the red zone and doesn't have to do that. So rather than do a leave, it does a pop RBP because RSP and RBP actually both point to the same value. Okay. We'll be able to see this in just a second. Oh, I see. Okay. Sorry. I see the stream is super messed up with the top and bottom here. I think I finally know why. Oh, there we go. I was too aggressive on my... Okay. All right. Yeah, so leave in simple instructions is 2 instructions. It is move RSP. Yeah, let me just write this down. Okay, so leave is equal to, and it's 2 instructions. So it is move into the stack pointer, the base pointer. So take whatever's in the base pointer. So basically move the stack pointer up to the base pointer. So copy the base pointer back there. And then do a pop RBP. So this pop RBP is actually inherent. So the one that's in callee, this pop RBP is inherent in both. And so this means that it's already done, but it doesn't need to do this move RBP into RSP because RBP and RSP point to the exact same value. So that's why that difference is there. Cool. Okay, let's walk through this. So you can actually see the epilogue, the prologue on main is these 3 instructions. The epilogue is these 2 instructions. The prologue on callee is these 2 instructions, and the epilogue is these 2 instructions. All right, so let's walk through this. So we have our code. We have our stack, all Fs at high addresses to low memory addresses. And we have our registers. So we have actually a bunch of registers that are used here. RAX, RDX, RSI, RDI, RSP, RBP, and RIP. This time we will just put the instructions somewhere. And I believe I took this from an actual run. So this was the real instructions when I ran this. So when I ran it, RIP was at 55, 55, 55, 55, 46, 11. So from somebody who was asking what that looks like, let me move my chair down. I'm not used to lecturing for, hours on end. But it's important for y'all to learn this stuff. So, okay. So first thing we're going to do, and then again, we need the stack. So when I ran this one time, the stack was at 7F, FF, 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 DD, 78. And that's just where the stack happened to be at that time that I ran it. So now we know that the RSP currently points to there, FDD78. Okay, and we also don't know exactly what the base pointer is, so this is just whatever thing was in there. We'll just put whatever that value is in there. It really doesn't matter. And okay, so we'll first do a push RBP. So, and what I'm doing here is each cell is 4 bytes. So 32 bits. So that way 8 bytes when we do this push. And that's because of how it's actually going to lay out all these things. So so the stack pointer is now FDD70, so it got subtracted 8. We now move this, because we've stored the base pointer, we now move the stack pointer into the base pointer. So now the stack pointer and the base pointer point to the same location. We then subtract, we're going to 16 from RSP. So we're going to save 16 bytes on the stack. We then move 28 into ESI. So 28 gets put into the ESI register. Then 10 gets put into the EDI register, into RDI. And now we've set up everything for the call to callee. So we've set up the first argument and the second argument by putting them in this registers. Now, what's going to happen once I execute this call instruction? So somebody walk me through what's going to happen. People are typing in Discord. Yeah, so the call does two things, right? So call will push whatever so it changes the stack pointer, pushes onto the stack whatever the location is after callee. So it'll be something like F 55555555 462, I don't know, 4, or it's not going to be 24, it'll be 25 or something. So it'll push that return address and it will jump to 5FA, which it knows is here. So it'll jump to that memory location. So that's callee is at 5555555545FA. I think it knows to go there. So yeah, that's great. It will push the return address, which is the address after the call function in main, and then it will start executing at callee. And the address after the call instruction is 4628. So that's what will get pushed onto the stack. So that gets pushed onto the stack. The instruction pointer is set to 45FA. And the bytes here that represent the saved return instruction pointer gets pushed onto the stack. Everyone good with that? Awesome. Okay, now the callee function executes. So now we push RBP. So again, and we don't know that main called us. We don't know what function called us. It could have been any function. It could even be ourselves. We could actually call our own function. So we're going to push and store the save base pointer. So we're going to push that onto the stack, push the save base pointer. So 7FFF, FFFFDD70 was what was in the base pointer. And then we're going to move the stack pointer into the base pointer. So now for our function frame, we're right there. We're going to move EDI into RBP -4. So this is creating actually local variables out of the parameters. So we're going to copy whatever was in EDI, the first, I believe is the first parameter, because we did callee 10, 4. We're going to put that in hex A is 10. So we're going to put that into RBP -4. And we're not going to freak out because we're writing over the lower than the stack pointer because we have the nice red zone. So we then are going to take whatever's in our ESI, which is the second parameter, which is 40. We're going to put that into RBP -8. We are then going to move RBP -4 into EDX. So that's going to be RBP -4. That'll be hex A into RDX. We're going to move RBP -8, which is going to be hex 28. We're going to move that into RAX. We're then going to take EDX, which is hex A, add it to EAX. So that'll be 32. And then add 1 to that, hex 33. Somebody, what's the decimal equivalent of hex 33? $51. Excellent. Cool. So yeah, we just put the return value into RAX in the RAX register. So now we're going to pop RBP. So again, that'll take the 8 bytes that the stack pointer is currently pointing to and put that back into the base pointer. So now we have, because we're in our function epilogue, right? So we have main's call frame on the stack. We have callee's call frame on the stack. We're going to pop RBP, which then changes and restores the base pointer from what it was. From what it was to FDD70, which is main's base pointer. Then we're going to return. So what did I say return was equivalent to? Pop RIP. Yep. Thank you. Excellent. So what that will do is it will add 8. It'll first what that will do is set RIP. So it'll change RIP to whatever the bytes are here on the stack. These 8 bytes, 0000555555554628. It will set that as the instruction pointer, and then it will increase the stack pointer by 8. So we should see that. And now this is that little breadcrumb. So this is that breadcrumb on the stack that we then go back to and start executing from. Then we do our 2 redundance lines. We move RAX into RBP -4. And now RBP is main's RBP. So the base pointer is set correctly. The stack pointer is set exactly where it was. We then take RBP -4, move it back into the RAX register. So that's hex 33. We do a leave, which was 2 steps. So the first thing of leave is copy the base pointer into the stack pointer. So that means the stack pointer will then move up to DD70. And it does a pop RBP. So then it puts 555555554630 into the base pointer. And now, what's at the memory location DD78? Yeah, who's RIP? Yeah, not whoever ran the program, whoever called main, right? Because main is just a function. Um, we As you get into this, you'll find out is there's another function, the libc. No, libc is not exactly correct. Yeah, there's somebody else that called us, and it's actually what sets the exit code of the program equal to whatever is returned from main. So it's the thing that actually does the syscall that we saw, that exit syscall. It tells the operating system, hey, we're done, but some cleanup may need to happen in there. Cool. And then we're done. So we just walked through the execution of one function, calling another function. So that's great. Questions on this? This is kind of important. Yeah, main colon is a label and callee colon is a label. Good question. What is the F5A in call exactly? Uh, that is, so calls and jumps in assembly are usually relative. So when you'd write it, when we would write assembly, you would write just call callee, and the assembler would figure out where callee would be located. So this is just a nicer way of it shows you, hey, I believe I want to say call instructions use relative addressing. So it says from the address that I am now, go backwards some certain amount, and that's where you'll start executing next. So it figures it out dynamically based on where that function is, and because the compiler knows exactly the number of bytes from that place to the location. But I can't, and then what it's showing you here is just the object dump. So this 5FA is like a nicety that it shows you. And then do all functions have a return? Ooh, good question. I believe so, unless maybe the compiler can prove to itself that the program calls, let's say, exit. And so, or the function calls exit, and therefore you have a function that is never returned from. So I guess you could have a function that doesn't have a ret. But yes, all functions that you want to return from should have a return instruction. Underscore start is typically the function that calls main. So but it's really defined in the elf. So in the object file itself of whatever the program is, that is what ends up calling main. So there's the entry point of the binary. Let me check. I think we should have an a dot out here. And I think it's read elf-s maybe. No, that's just those. How do I read elf? Is it just capital A for all? Yeah. So it's because it's in all caps. So inside of the elf header itself is what the entry point address. So it says, hey, you're going to start executing at whatever the hell is at 4F0. And usually when you compile this stuff with a libc and everything, it will be libc start main, which eventually then calls either start or main or whatever. So, but you can change that. Okay. What is the D word pointer? So this is the, yeah, it's a double word. So this means, yeah. So it means it's a 4-byte pointer. So when we're looking at it and we were writing assembly, we didn't have to include these because the assembler can infer, oh, you're using the EAX register, which is only 4 bytes, which means you only want to copy 4 bytes from memory into EAX. So when you write a program, you don't have to specify this. But when you use a decompiler, it usually will include these for you. Yeah, it's a more explicit way of doing it. Yeah, your compiler may yell at you depending on if you have size, like it'll say, hey, it's ambiguous what size you want here. So you need to tell me exactly what you want. But you basically don't need to specify until you, cool. Any more questions? Because we'll move on to our first buffer overflow. Did we talk about D words having different sizes or something? I think we've talked about technically a word can be different size, but I think in the way that we talk about them, it's usually 2 bytes. So then a double word would be 4 bytes, and a quad word would be 8 bytes. All right, we'll do this one more and then we'll. Okay, cool. All right. So, and this is what's kind of a crazy thing. So, the really kind of buffer overflows and these kinds of things, what we're going to look at is what is the implications of this calling convention that we looked at, specifically where saved RBP and saved RIP are stored onto the stack, right? Just as we saw. So it'll typically be when a function is called, it's first the saved RIP and then saved RBP and then any local variables of that program. And the thing you need to think about is the program itself has the capabilities to read and write to the stack, right? There's nothing that changes and modifies or protects you as a program from writing to your own stack memory, because that's the whole point of the stack, right? You need to be able to write to it and read from it. And so the question is, what would happen if you were able to change that? So here's a super simple function. So we have a function called myCopy. It has a so the way to read this, if you're not familiar yet with C, is we're passing it a pointer to some memory called string, str, and we're telling the compiler, hey, we want a local variable called foo that is exactly 4 bytes. So 4 bytes of space, and then we're going to copy string onto foo. So the way string copy works is it copies it keeps copying from one pointer to the other until it reaches a null byte. And so it will just keep copying. The key thing in here is we don't know how many bytes string is. String could be 4 or 10 or 100 bytes and more bytes than we were expecting here. And then we have our main function that is going to pass. So in C, the parameters get passed to main. argc is the number of arguments, and these are the actual command line arguments. argv is then the actual string that is passed in on the command line as the argument. So what this does is takes the first argument passed in, sends it to the function myCopy, which then copies from the string onto foo. And then we'll print out something that says after, and then returns 0. Cool. So we'll look at the compiled output here. So myCopy first pushes RBP, moves the stack pointer into the base pointer, subtracts 20 from RSP. Why does it subtract 20 when we only said we needed 4 bytes here? Nope. The answer is who knows. Compilers are freaking weird. All we know is it has to do 4 bytes, but it could do as many as it wants. And oftentimes, compilers will, for crazy optimization reasons, or on some CPUs and some architectures, memory can only be accessed at certain aligned offsets. And so, for whatever reason, it just decided to do this. So this is actually a good way to learn that, like, hey, you should always look at the binary itself, because if you look at the source code, you'd say, oh, there's a buffer on the stack of size 4, which means I just need 4 bytes and then I'm overwriting stuff. But that may or may not be true depending on how it's compiled. So here we're moving from RDI, so the first argument is a character pointer string, into RBP minus 18. Here we have our Q word, so that's definitely 8 bytes, it's a pointer. And then we're going to move that RBP minus 18 back into RDX. We're then going to calculate what is the value of RBP minus 4, put that into RAX, and then move RDX into RSI, move RAX into RDI. So we're setting up the arguments here to string copy. We're going to call the function string copy, and we have a, that's weird. Why is there a NOP there? I have no idea. Again, another thing. Why the hell does the compiler insert a NOP here? I don't know, because it wants to. Then we have our leave instruction and the return instruction. So what we're just doing here is so the important thing here is RBP minus 0 is that address is calculated, put into RAX, and passed as RDI, which is then the first argument to string copy. So that's where the destination of where we're going to be copying from the parameter that gets passed in string into foo. Yeah, it probably inserted it for a 16-byte alignment. But why wouldn't it do it at the end of the function? You think that this address has to be 16-byte aligns? Because it's only a 1-byte instruction. So why would it matter what the address is after call? Now, but you can add NOPs at the end of the function if you need to. I think I've seen that before, where there's NOPs in between in between functions. Why does it need to be before ret?
So the stack doesn't get messed up for when you do a pop.
This doesn't affect the stack at all.
Never mind. Yeah. I don't know. I've never actually seen it after a ret.
Yeah, I don't know. This is why it's so ridiculous looking at this assembly from what compilers actually do, but I did take this and I compiled this with whatever version of GCC this is. So yeah, you just say it's for performance reasons or because the compiler decided to, and then you can. It's not like you guys did MIPS, right? Doesn't MIPS have delay slots? On, like, I think branches and function calls. I can't remember, but oh, you didn't learn about delay slots? What? Is that in MIPS? I mean, it's probably CPU dependent, but yeah, because of the way that pipelining works on CPUs, oftentimes, yeah, on jumps or branch, a call instruction is basically a branch, but, or I guess maybe on conditionals. Anyways, on certain things, like even on the ret instruction, you could have one instruction afterwards that it would always do. And that's just was a little performance reason, but anyways. All right, cool, we don't have to get into that. All right, so the main function is gonna be very similar to what we had before. So we're gonna push RBP, move the stack pointer into the base pointer, subtract 16 from the stack pointer, then gonna move EDI, so the argv, so this is argv, the second argument will be in EDI, and we're gonna move that into RBP minus 4. Oh, weird, okay. Wait, no, yeah. EDI is the first argument, so that's argc. Anyways, so we move that into RBP minus 4, move RSI into RBP minus hex 10, we move RBP minus 10 into RAX, we add 8 to RAX, we then dereference, so this is where we're now fetching whatever RAX used to point to, now points to. We're going to grab that memory and move it into RAX, so this will give us this parameter here. We then move that into RDI to pass to myCopy. We then call myCopy. Then we do a load effective address of, oh, this is this constant string after RIP plus hex 95. So this is a position independent way of it to calculate these fixed locations, just like we had. And we used this technique when we were outputting data in assembly. So we copy that into RDI. We then move 0 into EAX. That's weird. Why do we do that? And then we call the printf function. And then we move 0 into EAX, leave and return to do our return 0. And again, if you spend too much time looking at this output of these compilers and trying to reason about why it does things, you will probably go crazy. So let's walk through this. So now we're running this program, so a.out, and we're passing in the string I space love space security 3 exclamation points. Am I passing 3 parameters to a.out or 3 arguments to a.out or 1 argument? Oh, it's almost like the stuff we did at the beginning of the semester was for a reason. Yeah, 1 argument. Why is it 1 argument? Yeah, all right. Squibbins got there first because it's in quotes, right? So being in quotes prevents the shell from interpreting it as multiple arguments and only as 1 argument. Cool. All right, so we have all of our code here. We have the different registers. So we have RAX, RDX, RSI, RDI, RSP, RBP, RIP. These are the registers that are used. It's kind of crazy. Even for a slightly more complicated program, this is something that is, we're still not using that many number of registers. So we have our stack. And again, just like before, I'm going to put in the values here when I ran this and debug this. So here at the start, the stack was at DD88. Our DI was 2, so that's the number of arguments. It's 2 because arg0 is a.out. The program that actually was executed, actually it's ./a.out. And then argv1 is the string I love security. So, and then let's see, the base pointer happens to be here, and RIP happens to be that value. So first thing we do is push RBP just like before. We then move the stack pointer into the base pointer. So now the stack pointer and the base pointer are both pointed to the same thing. Subtract 16 from the stack pointer. Now the stack pointer points down. We then move EDI, which was 2, into RBP minus 4. Again, this is another thing. Why is it doing that? We actually don't even touch argc. So why are we storing it as a local variable? Who knows? Maybe we need it at some point. It's probably just storing and copying all of the arguments to local parameters in case we need it again, because we'll be getting rid of these register values, so we'll get rid of them later. But anyways, interesting thing to think about. Why is it doing that? All right. Next thing, RSI is moving to RBP minus 10 hex, which is 16. So it moves that there. And I believe the way I did this, yeah, whatever. Okay. And then moving RBP minus hex 10. Oh yeah, dereferencing that. So saying, okay, where's RBP? No, it's just a move. Sorry. RBP minus 10, moving that into RAX. So that's going to move into the RAX register. We see we have DE68. We are adding 8 to it. So this is a pointer to argv. And since our argv was a character pointer, which means everything that it points to is the size character pointer, which is pointers are always 8 bytes. This means that to increment it to the next one, we need to add 8 to it. So that's what's happening here, is we're adding 8 to RAX. We then dereference RAX. So we take RAX, we look at whatever that memory location is there, which is argv plus 1. We move that into RAX, which is this string FE180. We then move RAX into RDI. This is the equivalent of argv1. We move that into RDI. So now we're setting it up and passing this as a parameter. And so now we're passing this as RDI. So this is the E180. And now we call my copy. So just like before, when we do call, we are pushing the next address on the stack, which is 46CE. We then need to store whoever calls us pointer. So we push RBP. We move the stack pointer into the base pointer. We subtract 20 hex from RSP. We now move RDI, which was our argument, into RBP minus 18, which was here, 7FFFFFFE180. We then move RBP minus 18 into RDX. We then calculate what is RBP minus 4, move that into RAX, DD5C, which if we look, DD5C is right here. So it's 4 bytes below where the saved base pointer is, which is 8 bytes below where the saved instruction pointer is. So then we move RDX into RSI. We move RAX into RDI. So now we're calling string copy. I believe RDI is the first argument. That was our local variable foo, DD5C. So we're going to be copying bytes from E180 and copying bytes onto DD5C going up the stack, because that's how we're copying the bytes of the string. And nothing in this string copy function, the only thing it's looking for is the source, which is I love security, until it gets to the end of there, which is a null byte. So string copy is going to happen. So we're going to essentially do, in the source, it was string copy foo string. Here, because we have the bytes, we know exactly where these memory addresses are. So we're going to string copy from E180 into DD5C. So the first one will go into DD5C. The next one will go into DD5, A, B, C, D, E, and then F, and then 0, and that will start overriding this DD6, what's at DD60. And that FE180 on our diagram is way above us. So if we look and if we use GDB, we can actually look at that as we're doing this. This is when I was doing this. So this is examine the string that's at FE180, and it would show you that it is the string that has the bytes there of that. We can actually look at the bytes and examine 19 bytes in hex at FE180, and it would show us, it should be I space capital L lowercase o v e space security 21 is exclamation point 21 21 21, and then the null byte 0. So this is when string copy will stop copying onto the local space on the stack. When you say can't see top, what do you mean can't see top? Oh, this very top here? I thought I fixed that. Well, whatever. It's okay. It's x/x and then this address. I'll post the screenshot later. I mean, the slides afterwards. Okay. Then we're, okay. So as this is executing, the 4 bytes I space LO get copied into these 4 bytes. And now we then overwrite the 8 bytes of VE space SECUR. And what stopped us from overwriting this? What stopped us from overwriting this saved base pointer on the stack? Oh, the answer is nothing. Nothing stops us. We just keep overwriting memory. until we're done. And the only reason we stop is because we got to the 0 byte of that string. And if we looked up the man page of string copy, we'd see that that's the semantics of string copy, is exactly that. So not only have we overwritten the saved base pointer, we've also overwritten the saved instruction pointer. So what happens? Does our program just blow up and crash and die here? Yeah, so the important thing to think about and to remember is after we do this overflow and we've overwritten those 4 bytes that were allocated for us, we've started overwriting other memory. At that point is not when it crashes. It actually crashes later. So we come back from string copy. String copy is like, I did everything you asked me to. I copied every byte from the destination string into the source string. From the source into the destination until I got to the end of the source string, and I'm done. And so now this executes. So then the NOP instruction executes. Then we do leave. So leave was copy the stack pointer into the base pointer, and then do a pop RBP. So it does that. Now the base pointer is 72, 75. So it's that part of the value that came from us that we overwrite. Now, now when it tries to return, it takes that value that's in there, puts it into RIP, and then goes, hey, what the heck? I don't know what memory address 21, 21, 21, 79, 7469 is. I have no idea what that memory address is. It doesn't work. It's a segmentation fault. And we should be able to see this. So by compiling this program, so you can take the C code, compile it with these arguments that I have here. So only one thing is actually possibly protecting you. You can run this with I love security. It'll say segmentation fault, which is exactly what we wanted. We can then use GDB on the program, run it and pass it that argument, and it'll say it's starting it, and it'll say that it received a seg fault at this memory address, which means it tried to access this memory at 21, 21, 21, 79, 74, 69, and was not able to do that. If we look at the registers, we can see that we actually, the value of 21, 21, 21, those are the exclamation points, remember? ITY, I think, is these ones, came from us because values that we as an attacker controlled got stored first onto the stack and then made their way into the instruction pointer. The other thing to notice is RBP. We actually totally control this RBP value. And so using this, if we can specify a memory address that we wanted the control flow to go to of the return instruction pointer, we can then trick the program to go execute any instruction in any code that we want. And that is a buffer overflow. So I talked a lot. I don't have, at this point, you actually have enough knowledge to be dangerous to start on either the Pwn College stuff. We can look at and go over some, actually triggering and executing buffer overflows and those kind of stuff. We can maybe look at that. I think, is next week finals week? I have very little understanding of what it's finals week, right? And then commencements after that. So
yeah,
we
finals
definitely
week is the next one.
We'll probably end up re-meeting at the next semester or something. But if you've made it this far, and I think there's a good 10 or so of you in Discord and another, I don't know, random hello strangers out on the Twitch land. So be proud of yourself. And this is the kind of stuff that, you now have learned enough to start being able to exploit low-level buffer overflow vulnerabilities with some additional information and stuff. But And with that, I don't have anything else, so we are done.
Oh, yeah.
Wow, you make them copy and paste this really long, terrible string in, Zion?
Hashes, man. Hashes.
Mm-hmm.
Yeah, it is pretty long if you're just typing it.
Oh, shoot.
All right. That is the end of the meeting. Like we said at the beginning of the meeting, we got a CTF this weekend. It's going to be run by Clasm, not myself, but you'll see a lot of familiar faces from the meetings there. So I totally, if you can make it, come and play. I know it's the weekend before finals, so